right, the next example we have, example 2, is to evaluate the given line integral, f dot dr over the path C, which is a closed path. And let's see. So let's just make a connection here. So I really think what I should have written here is, instead of C, is perhaps I meant to write the boundary of D. So let's go ahead and rewrite that. That way it makes sense how D comes into play. So, and D is the triangular region enclosed by those 3 vertices. So let's go ahead and sketch D first. I think that's a good choice. So we've got the origin, 0, 0. We've got 2, 0, and 2, 2. Something like that. Okay, so we got this right triangular region here. So let's go ahead and call that D. And the boundary of D, del D, like that. So, in this problem, we are not told to use Green's theorem or anything like that. So, do we have to use Green's theorem? No. But it's in this section, so let's think about it. And let's see why it actually is a really good choice to use Green's theorem here. So, if we just read this, they're saying to calculate this line integral. Well, what would we have to do to calculate this line integral? Well, if it's around the boundary of D, let's go ahead and orient this like this. Excuse me. What would we have to do? Well, we'd have to parameterize each one of these paths. So we'd have a C1, a C2, and a C3, which means for each of them we'd have to come up with their own R parameterization, so an R1, R2, and R3 of T. That means we'd have to take our derivatives of each and then do, essentially, we'd have to split this up into three line integrals. Not great. That's a lot of work. Hopefully I've just convinced you that that's a lot of work. Because this is a closed region, we can use Green's theorem. So for Green's theorem, what we're going to do here is we're going to take this line integral around the boundary of D, f dot dr, and convert it into a double integral of this quantity, del f2 del x minus del f1 del y dA, so a double integral over the actual region inside, the region enclosed by that curve. So you might think, isn't a double integral harder than a single integral? No, not in general. I know some double integrals that are very difficult, but I also know plenty of line integrals that are far trickier. So I think that's what we should do. So as a reminder, here we've got f1 for sine of x, f2 is x squared y to the fourth. So let's go ahead and fill this in at least. So this would be the double integral over D. Del f2 del x is 2x y to the fourth minus 0. There is no y in f1. Okay? So the double integral, so I'll even pull the 2 out to have 2 double integral over D x y to the fourth dA. Well, now we have to describe D. So we can describe D. Notice that it is both vertically simple and it's both horizontally simple. I'm going to go ahead and choose to do vertically simple. I guess. Or maybe doesn't really matter here. Let's just take a pick. The only reason I'm thinking maybe we should do horizontally simple is that way we don't have to raise something to the 5th power until the very end when it's a constant. So I guess let's try that. At this point, I honestly don't think one way is harder than the other. So this line here is y equals x, a slanted line. So if we're going to do this as horizontally simple, that means we're going to say y is between two constants. That would be between 0 and 2. And x is between two functions. So this right boundary, what's going to go here, this is just x equals 2. And what's on this side is x equals y. So this will be y. Okay. So we can go ahead and say 2 integral 0 to 2 integral from y to 2 of x y to the 4th dx dy. So 2 integral 0 to 2. With respect to x, we get 1/2 x squared y to the 4th between y and 2 dy. Well, this will become, I can cancel this 1/2 and this 2. And then what do we have? Well, we can just ignore this 1/2 now. 2 in for x squared, so 2 squared is 4. So this would be 4y to the 4th minus, this would be y squared times y to the 4th. So we'll have a total of y to the 6th. Okay. So doing all of this, what do we end up having? We end up having 4/5 y to the 5th minus 1/7 y to the 7th between 0 and 2. 2 to the 5th is 32 minus 2 to the 7th is 128. So whatever that turns out to be, which is 256/35. And that's the answer there.